energy theorem. And when we are removing energy from the object, we are actually removing the kinetic energy of the object. So K final minus EK initial will be equals to, and here we said we can replace this by final minus EK initial. But what is this? This is also the same as half mv squared final minus half mv squared initial. So this formula now becomes more simple to use. You can use amount of 5.7, and now we can square root both sides. So we get a v final will be equals to 2.39 meters per second down the plane. So this is how we can, after adding everything, we have that 3/2 v squared final equals to. Good day guys, welcome back to our YouTube channel guys. It's a new day, and Stifler is me, and me Stifler guys. So today we are on about work energy theorem guys. So after talking about the work net, it is important to talk about the work energy theorem. So before wasting any time guys, let's get straight to it. So guys, from grade 10 work, we explained that energy cannot be created or destroyed. So energy cannot be created from one form to the other. That's what happens when we are working with energy. We cannot create or destroy energy, but rather it can be transformed from one form to the other, or it can be transferred from one object to the other. So now we are going to talk about the work energy theorem. So this is a a transformation of energy, or a transformation of energy from one form to the other. That's why we talk about the work energy theorem. So let's get straight to it guys. So the direct link guys, it is this. when energy is added to the object, so when energy is added to the object, or when energy is transferred to the object. So when energy is transferred to the object, this is what happens guys. So when energy is transferred to the object, mostly it is transformed to be kinetic energy. So when energy is added to the object, it causes the object to do some work, and the work that it does most of the time, it is moving, so it is transformed to be kinetic energy. So when energy is added to the object, it is transformed to be EK, transformed to be kinetic energy. And when we are removing energy from the object, we are actually removing the kinetic energy of the object. So we are going to explore more about this kinetic energy relationship with the energy that is being added to the object, and we call it the work energy theorem. So let's take it that we're having an object that is here. This object is the work is done on this object, and then it moves this displacement, and then it is now here. So we know that this object was having initial velocity there, and when it gets there, it will have the final velocity, irregardless of what was the initial velocity or what is the final velocity, right? So according to equations of motion, we can calculate this by using Vf squared is equals to V initial squared plus 2 acceleration and then changing displacement, right? So if we rearrange this formula, right, If we take this side, we know that Vf squared minus V initial squared will be equals to 2 acceleration and then change in x, right? So we are trying to achieve something. So let's just multiply the whole equation by half m. So if we multiply the whole equation by half m, it means that this will be half m, and then we have our Vf squared minus, again we have our half m. So half m is actually multiplying everything, guys. So V initial squared. So this will be the same as, this will be the same as half m and then 2 acceleration changing like that, right? So half m is multiplied everything in the equation. So if this has happened now, it means that this becomes half mv squared final minus half mv squared initial being equals to, so half multiplied by 2, it will cancel out, so we'll be having ma changing x, right? But according to Newton's second law of motion, we know that F net is equals to ma. So F net is equals to ma. Instead of having ma here, we can replace it by this F net here, right? So F net is equals to ma. So having replaced that, here we know that half mv squared final is equals to ek final minus ek initial will be equals to, and here we said we can replace this by F net, right? But from the previous session, guys, we've explained that F net changing displacement, it is the same as saying work net. So now this side, ek final minus ek initial, we know that this is the same as changing ek. So putting everything together now, we can see that our work net is equals to changing ek. So our work net is equals to changing ek. So this is the work energy theorem. Work net is equals to change in ek. So let's put that in words, and also let's expand this formula so that you can be able to work with it no matter how complicated the situation can be like, right? So work net is equals to change in ek. So most of the times they ask, can you please explain the work energy theorem or state the work energy theorem in words? So we can take this straight from the formula. We can say that the work net done on an object is equal to, so the work net done on an object is equal to the object change in kinetic energy. So the work net done on an object is equals to the object's change in kinetic energy. So these, guys, you can place it in your own words, the way that you can understand it. The work net done on an object is equals to the object's change, which is this change in kinetic energy, and the work net done, which is this. So the work net done on an object is equals to the object's change in kinetic energy. So let's try to expand this formula and make it simple to use, right? So what is work net? Or we can rather write it like work net at first. So what is work net? Work net, we know that it is equals to F net changing x, right? What is it equals to? It is equals to the change in ek. What is the change in ek? It is ek final minus ek initial. But what is this? This is also the same as half mv squared final minus half mv squared initial. So this formula now becomes more simple to use. You can use this with this, or this with this, or this with that, or this with that. So no matter how much you can use it, you find the same answer, right? So this is the way of expanding this formula. We can also use it as work net is equals to half mv squared final minus half mv squared initial, or we can use it as f net changing x is equals to ek final minus ek initial. So however you can use this, it will still give you the same answers, right? So let's try to take a look at an example so that we can work this out, and I'll show you how to use this. So we're having this question there. They said a dynamic trolley of mass 2 kg is held at the top of the plane inclined at 30 degrees. So it means that our angle of inclination is equal to 30 degrees, right? And what else did they tell us? They also told us that the mass of this is equal to 2 kgs. So the trolley is released. So when something is released, it means that its initial velocity is equal to 0. When something is released or dropped, its initial velocity is 0. And rolls down the rough surface. So when they say something is a rough surface, so it means that there's frictional force. So the frictional force, they told us it is 6 newtons. And they said use work energy theorem to calculate the speed of the trolley after it rolled 1.5 meters down the incline. So it means that our displacement is equal to 1.5 meters. And the way that I used here, guys, it is very, very important. Write your information down so that you can be able to see what do you have and what you don't have. So the question here was to use the work energy theorem to find the speed. So it means that we're trying to calculate the final velocity when this has moved 1.5 meters down the inclined plane. So just like always, guys, I always advise you to start by drawing a rough free body diagram so that you can see the situation. So they say this is inclined at 30 degrees. So this is our trolley. So which forces are obvious? We know that there's normal force that is obvious, and there's Fg as well that is obvious, and this thing is moving downwards, so it means that our frictional force will be up the plane. So this is our frictional force, right? And again, I also advised you that if any force that is going towards the motion, so if the force is going towards the motion, give it a positive sign. If it is going against the motion, it should be negative. So in this case, our frictional force will be negative. And the other force that we are having that is going to plane, it is Fg at x, or Fg parallel. So this is Fg at x, or some can call it Fg parallel, right? So they said we must use the work energy theorem. So firstly, let's write it. It says work net is equal to changing Ek. So there's a mark for just writing Ek. Work net is equal to changing Ek. So next, we are going to expand now this formula so that we can be able to work what we need. What we need here, it is the final velocity. So it means that we can now say our work net is equal to F net changing that being equals to half mv squared final minus half mv squared initial, right? So what is our F net now? So we can calculate our F net somewhere else. So F net, which forces do we have? We have Fg parallel. So what is Fg parallel rather? is equal to mg sine of theta, and our theta is this. So this becomes the mass, which is 9.8 sine of 30, and this gives us 9.8 newtons, right? So our F net now, we said our FG parallel is going down the plane, so it should be positive. So this means that this is 9.8 plus our negative frictional force, which they told us that it is 6, right? Multiplied by the displacement, they said it is 1.5. This should be equals to half the mass being 2 v squared final, the one that we are trying to find, minus half 2 and then 0, because initial velocity was 0 because this was released, right? So it means that all this can sums up to 0, right? So multiplying this here, this is 3.8 multiplied by 1.5. This should be equals to v squared final. And now our v squared final will be equals to, after doing that, we can get the amount of 5.7. And now we can square root both sides. So it means that our v final will be equals to 2.39 meters per second down the plane. So this is how we can use the work energy theorem to find our answer, right? Maybe let's do another example so that you can be okay and you can learn how to use it perfectly. Okay. So let's have this example. It is saying a 3 kg remote controlled car. So already we know that the mass of this is equal to 3 kg. Is driven up a plane inclined at 25 degrees. So it means that our angle is equal to 25 degrees. The car's motor exerts an average forward force. So it means that this is our applied force of 60 newtons. And don't forget that this car is driven up the plane, so it means that it is going up, right? And it experiences a constant frictional force of 15 newtons. So this is our frictional force as it moves up the inclined plane. The speed of the car at the bottom of the inclined plane is 5 meters per second. So this is our initial velocity being 5 meters per second. Use the work energy theorem to calculate the speed of the car after it traveled 4 meters up. So our displacement is equal to 4 meters. Now we're just trying to find our final velocity then, right? So they said you must use the work energy theorem, which is also very, very simple, guys. We're just going to apply what I taught you, right? I said first thing first, we must draw our free body diagram. Even if they didn't ask on your question to draw the free body diagram, you can sketch your free body diagram on the side so that it can help you to understand which forces are going which side and how is the situation like. So let's see. So we are going to draw our free body diagram like that. So this is 25 degrees. So this is your object. And again, we just put normal force, Fg, and this now is going up. So this is our force applied. We're having the frictional force, just like that, right? So now we are having the situation when our object is going up the plane. So our object is going up. So our up should be positive and our down the ramp should be negative. And now let's check which forces are working to the plane. So there's force applied, it is working to the plane, there's frictional force, and there's also Fg parallel or Fg at x, right? So we should know that our force applied, it is positive, our frictional force, it is negative, and our FG parallel, it is also negative because they are going down the plane. So this one is having a component FG parallel. So now let's try to find what we are told. So whenever they tell you to use the work energy theorem, you just start by saying work net is equals to change in EK, right? So on our work net, what are we having? So this work net is equals to F net, like that. So this will be equals to half mv squared final minus half mv squared initial, just like that. And then from there now we can try to expand this. What is our F net now? It is the sum of all these forces that are acting parallel to the plane. So this can be force applied plus minus frictional force plus minus FG parallel multiplied by the displacement, right? Will be equals to half mv squared final minus half mv squared initial, right? So our force applied here, it will be equals to what? 60 plus the frictional force, which is going in the opposite direction, and then FG parallel, we can calculate it. FG at x is equals to mg sine of theta. So this is 3 by 9.8 by sine of 25, right? So we can place it that. So this is 3, so this should be negative 3, 9.8, and then sine of 25. So we can close that, being multiplied by 4 meters. So this is 4 meters, being equals to half the mass, which is 3, the final velocity, which is unknown, minus half 3, and the initial velocity, which was 5, just like that, or 5 squared. Yes, 5 squared there. So what do we have? So this side we are going to have a situation like after multiplying everything, we're going to have 130 comma 3000 being equals to 3 over 2 v squared final minus 37.5, right? So we can take this that side. So after adding everything, we have that our 3 over 2 v squared final will be equals to 167.8, and it means that we can multiply both sides by 2 over 3. We can multiply it by 2 over 3. So it means that our Vf squared will be the same as multiply by 2 over 3. We get 111, 87, and now we can just do the square root both sides. So this square root, this square root. So we can find out that our final velocity will be equals to what? So our final velocity now, it is equals to 10.58 meters per second. So this our final velocity now, it is 10.58 meters per second. Okay guys, I hope you have seen how this is done, guys. So having said that, I'll leave you with a checkpoint 2, which we can do on the next time that I'll be doing the checkpoints, but try to do them, guys. They'll help you a lot. So having said that, guys, I'll see you on the next one. So if you haven't subscribed, please subscribe, and also share this video, and also like this video, so that like it can help us keep creating content like this. And if you have any topic that you would want me to do after this, you can send me an email at this email, or you can go to my bio. There's also the email address that is there, and there's also my WhatsApp that is also there. You can also click on the link and you can send me any topic that you would want me to do next, or any question in particular that you are having a problem with, and I will deal with it right here, guys. So having said that, see you on the next one.